Alright, so let's move on to 22.5. This video probably is not going to be that long, and most of what we learn is going to be pretty straightforward. So again, I think this chapter and the next one are pretty easy to understand. And so we're going to talk about the Friedel-Crafts acylation, and we already talked about the Friedel-Crafts alkylation. Whenever we do the alkylation, we use an alkyl chloride, and so some type of sp3 hybridized carbons with a chlorine attached to it. In the acylation, we use acid chlorides. So remember, in the last exam material, we learned how to make acid chlorides from carboxylic acids. And so we can derive these from a variety of different starting materials. So what happens is we end up putting these carbon groups onto our benzene ring. And so we get a product that looks like this. And so the mechanism is extremely similar to the Friedel-Crafts alkylation. So let's run through that really fast. We're going to use aluminum trichloride as our Lewis acid here. Remember, you could use iron trichloride as well. And I'm using this simple acid chloride here, but there could be any other carbon stuff attached to it, and the same reaction will occur. Just like we saw in the alkylation reaction, we get coordination between our chlorine and our Lewis acid. Since chlorine now has two bonds, it donated one of its lone pairs. It gets a positive charge, aluminum gets a negative charge, and now this chlorine just pops off in a heterolysis step, just like we saw in the alkylation. And so then we get this positively charged carbon here, and so this acts as our electrophile. Remember, benzene's not that reactive, and so we need to make our electrophile much more reactive. This is formed because of the resonance stabilization. And so this has a corresponding resonance structure that looks like this. This goes on to participate as your electrophile in your reaction. And so we get attacked by the benzene ring. And again, when we're just using benzene, it doesn't matter which carbon it swings out on. We'll talk about in the next chapter where we have other substituents in our benzene ring, which way it should swing out. We generate this carbocation here, so we have taken aromaticity away from our system, and we need to bring it back. So we do an elimination reaction. And so we lose HCl in this process, and we get our acyl group on our benzene ring. So this is the Friedel-Crafts acylation. All right, one thing to note about the Friedel-Crafts acylation is whenever we generate that carbocation on the carbonyl carbon, because of the resonance stabilization with the oxygen lone pairs, we do not get carbocation rearrangements. And so this is an advantage over the Friedel-Crafts alkylation. So if we wanted to make a molecule like this, looks something like this. So you might be thinking, okay, maybe a Friedel-Crafts alkylation reaction. I think backwards, I can make this carbon-carbon bond from the alkylation reaction. And so I would take my benzene ring, I would take my corresponding alkyl chloride, like this, and then I do my Friedel-Crafts alkylation with my Lewis acid, and I'm going to make my bond. Remember, whenever we do this, we essentially pull off the chlorine, and so in this case that would generate a primary carbocation, which would very quickly do a 1,2 hydride shift with the hydrogen on this carbon, therefore giving us the carbocation here, and then that would serve as our electrophile in our Friedel-Crafts alkylation reaction. So our product from that would be this one shown here. So see, this is not the desired product as this one, and so we should think about a Friedel-Crafts acylation reaction. So instead, we go back to this. We think, okay, we can do a Friedel-Crafts acylation. That's going to put a carbonyl at this spot. And then we know how to reduce carbonyls down to CH2s using the Wolff-Kishner reduction, the Clemmensen reduction, or the Raney-Nickel reduction. So again, think backwards from there. So we get back to these two intermediates, so benzene ring and then our acyl chloride. And we know that once we make that carbon-carbon bond, we're going to have to reduce the carbonyl with the Wolff-Kishner reduction, for example. And then if we don't have the acid chloride to start with, remember we can make this from the carboxylic acid. And so we have something like this. And then remember, we know how to make carboxylic acids from the oxidation of alcohols and things like that. And so we could continue to work backwards to the desired starting materials. All right, so we'll move on to 22.6. We're going to talk about nitration. So you did the nitration reaction in the lab about a month or so ago, and now we're going to talk about it here in lecture. So we take nitric acid and sulfuric acid, and this ends up putting a nitro group on our benzene. And so this is our nitration reaction. We'll then look at later in this chapter how we reduce this to an amine, and so these can be used as synthetic intermediates. For the mechanism of this reaction, we want to generate an extremely electrophilic electrophile like we've been doing the entire chapter. So both of these things are not highly reactive the way that they are right now. And so the sulfuric acid ends up protonating the nitric acid to help facilitate the generation of the electrophile. So we draw out nitric acid. We have something that looks like this. So our nitrogen has 4 bonds, so it's a positive charge. This oxygen has 1 bond, so it's a negative charge. So overall, our molecule is neutral. And we end up protonating this from the sulfuric acid. And so now we've generated H2O over here. We know that's an excellent leaving group. And so these electrons from this oxygen push down, and then we kick out water. And this generates our NO2 electrophile shown here. So once we're at this point, this serves as our electrophile in our reaction, and we go through the exact same mechanism we've been seeing. And so I'm going to erase this stuff so that I have some room, redraw my electrophile over here, and we'll use benzene as our nucleophile. And so we end up with an intermediate that looks like this. Our benzene ring attacks our nitrogen. That would mean nitrogen would have 5 bonds at that point, and nitrogen never has 5 bonds, so we move those electrons up onto the oxygen. Now we have this structure over here where we have the positive on the nitrogen, negative on the oxygen, so overall this group is neutral. We've taken away the aromaticity of the benzene ring, so we have this carbocation, and so we have to deprotonate that. Remember that we kicked out water earlier when we made this NO2 electrophile, and so water is going to pick up that hydrogen. And then that gets us to our final product. All right, so we're going to move on to 22.7, talk about sulfonation of benzene rings and desulfonation. So in the previous reaction for nitration, we used nitric acid and sulfuric acid. In this reaction, we only use sulfuric acid, and we put this type of group on there. So this is the sulfonation reaction. We get SO3H on there. And then desulfonation, this reaction is actually reversible. And so if we put in a bunch of water and acid, which I'll just write as H3O+, we can actually get back to the benzene ring. And so in the next chapter, we'll look at how we use sulfonation as somewhat of a protecting group, so we can protect a certain spot on the benzene ring and then open it up later back to the hydrogen if we would like to do so. So I'm going to run through the mechanism of the sulfonation reaction. I'm not going to talk about the desulfonation, so I won't expect you to know that, but I do expect you to know that this reaction will occur when we use excess water and acid. So again, we take our sulfuric acid, we have a bunch of that floating around, it ends up protonating itself within the solution, so the reaction mechanism is very similar to the nitration. So in step one, just like we saw in the nitration, we get protonation here so that we can generate water. So now we have an excellent leaving group, and then just like before, we're going to take the lone pair on this oxygen, we're going to kick out the water. And now this oxygen here has 3 bonds to it, so it has a positive charge. We could draw a resonance structure where the positive charge is on the sulfur. And so this is the species that serves as our electrophile, and our benzene ring can attack this. So now the rest of the reaction mechanism is exactly like what we've seen before. The benzene ring will come in and attack this. We're going to move those electrons up onto the oxygen here. Since it's just benzene, it doesn't matter which side we swing out on. And so we get to an intermediate that looks like this. So this is SO3H, so we could just write it like this, so we don't have to draw it out. We've lost aromaticity in this process, so we're going to regain aromaticity. We lost water here, and so just like in the nitration reaction, the water is going to come pick off this hydrogen. And so then we get to our final product here. So this is the sulfonation reaction, and then remember we can desulfonate if we use excess water and acid. Alright, so let's go through a practice problem. So we want to make the following molecule from benzene. So we need to think backwards to benzene. We know this ring right here is benzene, and so at some point we're going to need to make a carbon-carbon bond here, since this is one of our required starting materials. So we've learned several reactions so far this chapter that would allow us to make this type of bond. One of the ones we learned the Friedel-Crafts alkylation, and we learned the Friedel-Crafts acylation. In this case, you can see this carbon's only attached to one other carbon, and then the rest of the chain. And so if we did an alkylation reaction, and we put our alkyl halide on that carbon to give us something that looked like this, the aluminum trichloride or iron trichloride, whichever Lewis acid we use, is going to pull the chlorine off, giving us a primary carbocation, which is quickly going to do a 1,2 hydride shift to give us the secondary carbocation. And so a Friedel-Crafts alkylation is not going to work in this case. So remember, Friedel-Crafts acylation is the way to get around the carbocation rearrangement and then do a Clemmensen reduction, for example, to knock off the resulting ketone. And so we think backwards like that. We're going to need something that looks like this. Remember, we could take acid chlorides and make esters using alcohols, and this would be no different in this molecule here. And so what we really need to do is have a protecting group on this oxygen so that it doesn't participate in the reaction. And so we would need something like TBS, for example, so tert-butyl dimethylsilyl, which we talked about earlier in the semester. And for the purposes of this question, make from benzene, this would be an appropriate starting material. We would then do our Friedel-Crafts acylation, clip off this carbonyl using a Wolff-Kishner reduction or Clemmensen reduction, and then clip off the TBS group using TBAF. And so that would be in the forward direction. Another reaction we learned this semester, or this chapter, is how to do halogenation on a benzene ring. So we could think about making something like this, and then turning it into a Grignard, for example, so that it could serve as a nucleophile. And then we would need to make this carbon electrophilic, and so we could just put a bromine on there. And so we would get back to something like this. Remember our oxygen, again, we don't want it to have this OH on there because it can serve as a source of a proton. If we have a strong enough nucleophile slash base, it can just deprotonate it. Or it can serve as a nucleophile, so you just want to protect that. And then we want to work backwards from here to get back to benzene. So in the forward sense, you could take benzene, do a bromination reaction like we learned the first part of this chapter, use magnesium to turn it into a Grignard reagent, do an SN2 reaction, and then TBAF to clip off the protecting groups. So don't forget about your protecting groups. Anytime you're making a Grignard or a strong nucleophile, it can potentially deprotonate alcohols, so OHs, or amines, so NHs, or carboxylic acids. So